Hi, everyone, and welcome to today's episode of Where Does Your Journey Stem From, hosted by myself, Dr. Karina Minardi. Today, we are so fortunate to have a researcher, a graduate student researcher from Indiana University, Brianna. So, without further ado, let's welcome to the stage, Brianna. Hey, Brianna, how's it going?
Hi, I'm good. How are you?
I'm doing well. So again, thank you for joining us. And Brianna is pursuing a PhD in chemistry at Indiana University, focusing on materials and organic chemistry. She's a third-year graduate student in Dr. Liang-shi Li's lab and an NSF-GRFP Fellow. So we've had a couple of fellows already on our episodes. Previously, she received a BA in chemistry from Colgate University. Her current research focuses on developing an alternative cancer treatment by synthesizing a new photosensitizer, a molecule that can absorb light and be used in photochemical reactions, to be used in photodynamic therapy, where light is shined on a photosensitizer to destroy tumor cells. Really, really cool. Ideally, the treatment will be more localized than current methods to minimize patient side effects, as we all could imagine. She also co-founded and is president of a club called Science Looks Good on Anyone, SLGA, that encourages younger students to build interest and confidence in STEM through science outreach, mentorship, and communication. And that's, again, something that we're also passionate about at Stelpram. The club performs demos and leads hands-on labs for students. So I'm really excited again to not only have you on an episode, but also to network with you. But there's only so much information that you can glean from a bio. So I'm curious, tell us a little bit more about Brianna.
Yeah, thank you for the introduction. So like you said, I got my bachelor's from Colgate University. So right after high school, I went there. I started actually interested in physics. And then as I learned more about the research and stuff that's being done, I aligned more with chemistry. So I switched to a chemistry major. And then I actually worked in a research group while at Colgate as well, and it was on chemotherapy drugs, so I stuck with the cancer theme. And after that, I worked at the Wisconsin State Lab of Hygiene for a little bit as a chemist there before coming to grad school. So I took 1 year off in between. But it was really cool to kind of get to experience what you can do with a bachelor's. But ultimately, I decided I wanted some more autonomy in the lab and stuff. So that's why I decided to come back for my PhD.
So there's a lot there that I want to explore. I love that you pivoted from physics to chem. Similarly, I pivoted from bio to chem. And it was really the research. It wasn't the course curriculum that really was pivoting for me, or pivotal for my pivoting, to be utterly redundant. So tell me a little bit more about, what was physics alluring to you? And then kind of what was that moment in which you said, this chemistry thing is actually kind of cool?
Yeah, I think in high school I had taken AP Physics 1 and 2, so I had taken more of those classes than chemistry, and I was a little bit torn, but I just really I like math and stuff, and there's more of that in physics at that level. So that's why I originally started there. And then as I looked into the jobs with physics and then the research and stuff like that, that was a similar thing for me where I was like, I have always really liked medicinal applications. And the potentials for chemistry tend to be greater than in physics. So I kind of decided to switch for that reason. And I liked both. But I like being able to create things and stuff that chemistry allows you to do.
I can appreciate that for sure. It seems sometimes, and that's definitely sort of one of my things that I like to emphasize, at least in our organization, as well as this podcast, is that not everyone is necessarily suited for every field. And just because you're really good at math does not necessarily mean that you would like physics, or something to that effect. And the other thing I think that's really interesting is your sense of drive to an application base. It's sort of mission driven work, which is really critical.
Yeah, that's something, because even in chemistry, different fields focus on application more than others, and that's something that has always been really important to me personally, is I care about the product I'm making or the application it has. But there's other really important areas, like if you're purely organic and you do just organic synthesis, where sometimes you're focused on just learning more chemistry so that it has numerous potential applications, but you don't necessarily know what that is, or you don't see it through that far. Whereas I kind of like to be closer to the product and the application that I'm actually doing, but it's just preference.
Yeah, of course. And it's where you also, where kind of you, if you like building things, but then you don't necessarily like having them come to market or so on and so forth. Speaking from like an industry background, that's really critical. So you also mentioned that you took a year off, which I'm a huge fan of. I also took a year off. And I want to learn a little bit more of what you were doing, and then sort of what illuminated the desire to then go back into grad school.
Yeah, so I think for me, I didn't know a lot about grad school going in. For me, like I'm from a really small town, so nobody really does that. Nobody goes to grad school. If you go to college, it's just a bachelor's. It's like a 4-year degree. So I hadn't really thought about it until I got to undergrad, and then I didn't really understand what it was, and the thought of like more schooling was kind of intimidating. So I kind of just sat back, took the year to really think about what I wanted to do. And then using my bachelor's degree, I realized that the roles I could get with that, I wouldn't be able to explore my own ideas. And I was kind of just following procedures and not really given any autonomy or able to be creative and stuff in lab. And that was part of why I love chemistry, is I love thinking about it, coming up with ideas, testing them. So for me, just being in the lab, I was like, I don't see this long term. It was a great job, but long term for me, I wanted some more autonomy. So that's why I decided to go back.
No, I love that. I think when you think about, a traditional laboratory environment that has, rote SOPs, it really is fitting for a personality, again, fitting for a personality and proclivities of like, okay, I'm okay with constantly doing the same assay every single day and getting either positive or negative results, and to what extent. But then there's also this flip side of like, and I had another episode of a guest who actually is a neighbor of yours, Purdue, Vanshika, and she talked about creativity in the lab, and that she's artsy and she loves art and dancing. And one of the things that she loves specifically in a laboratory environment is that creative solutions, and that she can be creative.
Yeah, I definitely agree with that. That has been, like, I always thought I really liked chemistry and everything, but I think I like it even more now. And I'm definitely determined that this is the right path for me because of that. Because once you get to this graduate level, that's when you're really able to be creative. Because before then, you almost don't know enough to come up with like really good ideas and novel ideas. But as you learn more and then you start to get to think of these things, I think that's been really cool, is being able to test my own ideas and be like, wow, I came up with something that worked. That's kind of a cool feeling.
Or on the flip side, I came up with something that actually gave me a negative response. And it's like,
Yeah.
I thought I was going to get a positive response. Why? I always, reflect on my time in the lab, and it's like when things broke were actually the times in which I learned the most. Because it was not only did I have to then say, how did it break? But then how do I fix it, especially in an instrumentation lab? And how do I either not do it again or change it so that it doesn't happen again? So things like that, which is always fascinating.
Yeah, that's definitely true. I do a lot of synthesis, so the number of times reactions don't work sometimes outnumbers the time that they do. Um, but you get to learn a lot, and then you get to figure out why it's not working, how to make it work, or a different route or something like that. And then, yeah, that kind of gives you a platform for creativity. And definitely when I was at the state lab where it was SOPs, I used to secretly say that my favorite part was when it failed for some reason, because then I got to think and I got to be like, what's going on, what's different this time, that kind of a thing, instead of just doing, okay, this step, this step, this step.
So I do have a question before we start into your current research and current graduate path. If we think about, you initially went into Colgate for physics, and then you pivoted to chemistry. Like, and you talked a little bit about AP physics, but really, what was it as a kid that drove you into the pathway of STEM? Like, was there a time point? Was there a person? Was there an event?
Yeah, for me, it started really early. My dad was a high school science teacher, so I kind of grew up in just with him. We'd be like on our tricycles down the hallways and stuff. And then slowly, as we got older, he would show us the labs that his students were doing and let us do them in a safe way, and kind of prompt us to ask questions. So even when we were little, I remember like sometimes we'd be in the kitchen and he would do like a little experiment and ask us, be like, what do you think is happening? And he'd have us come up with guesses and he'd be like, okay, how could we test that? How can we figure it out and stuff like that? So he really kind of built that scientific inquiry really young for me and all my siblings. We all kind of went into sciences. So it definitely was effective for that. But yeah, so it really just made me ask why a lot more than I think I would have had if I had a different, or if he had a different job, I guess.
I totally love that. That is, that's so endearing on so many levels. And I'm sure he's proud then that you're, taking it to the next step, right? So I guess the $1 million question, and I don't have $1 million to give you, but I'll ask it anyway, is, are you going to become a teacher? Are you going to become a professor?
I have definitely considered it. If I'm being honest, I haven't fully landed on what I want to do yet. I kind of like a lot of different things, which is a plus and a con at the same time. But yeah, so I've definitely considered it. I like a lot of aspects of it. There's also some pros to working in industry and stuff. So I have not decided.
Neither have I. So, I think that's totally fair. And I don't know. I think that's fine. I was just thinking, I was like, are you dead set on it because of, familial, whether it be stressors or passions or whatever. So that's fun though. And you know what? A non-decision is still a decision. So, hey, whatever. The world is your oyster, right? So now you're at Indiana University. You were pursuing a PhD. You said you just came off of your quals, so congratulations.
Thank you.
So tell us a little bit about sort of the high overview of what your research is, sort of goals. I think we alluded to it obviously in your bio, but I want to hear it directly from you.
Yeah, so overall, I'm looking at making a new photosensitizer for photodynamic therapy. And photodynamic therapy is a really cool alternative cancer treatment. And so basically, it uses light shined on the tumor to activate oxygen. So there's an energy transfer that happens from the photosensitizer to oxygen to generate this reactive oxygen species. And that can then kill the tumor cell essentially. So if you can localize the photosensitizer to the tumor site, it's sort of dually localized and minimizes side effects for patients. And it has been approved in some clinical trials, but there's limitations with the current photosensitizers. So new photosensitizers are being developed to just improve this and make this a more widespread treatment. So for mine, I'm using these things called graphene quantum dots, and they're basically a single sheet of graphene that I synthesize stepwise to make sure that it's atomically precise, and then I make them water soluble, and hopefully I can make them localized to the tumor site, where then I would shine long wavelength light, and long wavelength light is desirable because it has greater penetration depth. So if you can use longer wavelengths, you can actually treat tumors that are deeper into the body and also larger. So that's one of the big drawbacks with photodynamic therapy is this penetration depth. So I'm looking to expand that so that it can be used on more tumors.
So you talked a little bit about current clinical trials that are using photodynamic therapy. What are the, what is the oncological sort of areas on the body that they're looking at? Because I think that would be, it's one thing to have photodynamic therapy done on the skin. It's readily available. It's accessible. It's right on the dermis. I mean, it's but it's another thing when it's actually in deep tissue. So talk a little bit more about that.
Yeah, so that's where that penetration depth comes back. So there's a few photosensitizers approved. They all treat different types of cancers based on the location in the body. Like you said, the skin is easily treatable, but we're looking at being able to treat deeper tumors. And then the type that it targets is also dependent on the photosensitizer. So it kind of depends at which one you're looking at. But right now it's mostly restricted because of that penetration depth.
And you said a little bit about graphing quanta dots and making the sheet.
Yeah.
Make sure that I'm actually translating what you're saying. So would you ideally, and I mean in an ideal situation, wrap the tumor in that, or would you actually coordinate the explicit locations where you would put the dots?
Yeah, so with that, I start with a small molecule to make the sheet, and then it creates, they're still small, just like a few nanometers in size, and then hopefully they will target the tumor, so they'll concentrate there, and because there's more at the tumor site, and then you couple that with the light, then it's only activated at the tumor site. So it would just be there in higher concentrations. If you can penetrate the cells, you need to get it fairly close because the reactive oxygen species is very short-lived. So it does have to be pretty close to the tumor, if not inside.
So I'd be curious, what is the current thinking on delivery then? I mean, is it like an injectable to the tumor site? Is it an ingested pill form? I'm just curious.
Yeah, so that's a whole other question that we'll have to answer once we get there. So there's different ways to do that. There's different targeting groups you can attach and a bunch of different routes you can explore. Right now, we're in very early stages. I'm kind of starting off this project. So we're focused on finding the right graphene core size for that longer absorption for the penetration depth. So we're at that stage still right now. But once we figure that out, we know the size, then we can start looking at what groups we can attach for targeting purposes.
So how do you measure the core size?
So because I synthesize it stepwise, then I know like exactly what the structure is versus letting it self-assemble or anything like that. I know exactly what the structure is. And it's characterized by NMR for the most part until the later steps.
That was going to be my next question around instrumentation. Like, how do you actually quantitate the sizes and or characterize it? Plus, I would assume there would have to be some sort of purification too, right?
Yeah, so it's column chromatography, NMR, up until the last 3 steps. And then I have a size exclusion column, and then just precipitations for purification. And then we switch to MALDI-TOF once it's really big.
That's really cool because you're taking analytical principles, right? So column chromatography, you're doing MALDI-TOF. Size exclusion is a little bit different and uses kind of different principles, obviously. And then you're using NMR to look at, I assume, where your protons are in relation to everything, and then be able to actually quantitate, where you have spacing and what your core sizes are. So you're using a lot of like tools in your tool chest after your synthesis, and even the synthesis is using a lot of the tools in your tool chest, I would assume.
Yeah, that's one of my favorite parts about the project is I get to kind of wear so many hats. I get to do like all the synthetic techniques and then some more like organic synthetic techniques and then material synthetic techniques as it gets larger. And then after that, I am doing some photochemical studies on it. So I'm looking like using a fluorimeter and stuff like that to see where it's absorbing. Well, UV vis to see where it's absorbing and then fluorimeter to see where it's fluorescing. But
you can't be an organic chemist synthesis without having UV vis, I think.
Yeah.
That's for sure. So does your lab there's a couple of ways that labs like this kind of organize. Either they have a specialist, their specialty is sort of the synthesis piece, and then obviously the quantification, qualification of what they're actually generating. Or they have sort of the end to end. So they have anywhere from the biostatisticians, I don't know why you would need a biostatistician, but it just came to me, a statistician, all the way to sort of the application sciences or scientists who do sort of the application work based off the cells. So where kind of does your lab fit in it, and or do you have collaborators?
Yeah, so we're a pretty small lab. There's just a few of us in it. So we wear a lot of the different hats ourselves, and then we do have collaborators for things that are outside of our purview. But basically the common thread in all of our projects is these graphing quantum dots. And I'm the only one who's using them for reactive oxygen species and photochemical purposes. Other people in my group are doing like electrochemical reduction of CO2 and stuff like that.
So when you were thinking about grad school and you were thinking about grad programs, how did you go about selecting this as a research topic?
Yeah, honestly, it was the interdisciplinary nature of it with the medicinal application. So I really liked the application of it. And I saw that I got to do a lot of different things, learn a lot of different areas of chemistry, because I get to do some physical chemistry, some organic. And that was really appealing to me. And then I've also always just really liked using light to do things because it's just fun. So I liked being able to do that with such an important application.
So what is, when you look at the next year, sort of what are your research hypotheses and or foci on where you want your research directionality to go?
Yeah, so I'm hoping to start wrapping up some of the synthesis and then looking at how the properties change as the structures get bigger, and then if I can see any optimization of the reactive oxygen species at longer wavelengths with that extended conjugated core. And then from there, it will be what's the best way to make sure it's completely water soluble, not aggregating in solution, and then we can start just quantifying the amount of singlet oxygen generated and stuff like that. But it's a long ways off from clinical studies.
Yeah, no, I was just curious about, no, I like it that it's both a methodological approach, but then also a optimization piece, right? Is that, yeah. I think that's really fascinating. And I think it speaks obviously to the analytical nature of myself, of like, I love precision and making everything optimized. That's just my trend. So I can appreciate that. So that's sort of what the outlook looks at. Like what keeps you up at night around this work?
I think I'll probably go back to the like creativity and stuff. Like when I've had ideas that like I'm cooking, and then all of a sudden I come up with an idea for a new route or a new reaction I want to try or something like that. And that's really exciting, of like, oh, what if we did this or changed it? And it's usually not drastic things, but I'm like, what if I explored this or modified this a little bit? So I think I'm just kind of always thinking about it because of that autonomy and being able to be creative. And I like being in lab. I like setting up reactions and doing all of that, making new things. So I think kind of just all of it.
I don't necessarily know if that's a good thing that all of it keeps you up at night, but good, maybe? I don't know.
Yeah.
No, but I mean, that's really cool. But then you also have, your club. So I wanted to ask you a little bit about, what do you do? What is it? Obviously, we'd already talked about Science Looks Good on Anyone club. So I'm just curious if you could speak a little bit to it.
Yeah, so I started that with one of my friends here. And our main thing that we do is we go to a local high school and we have a 10-week program, and we lead a demo to start off, and then we do hands-on labs with them. And they're all like simple, using kind of everyday materials, but just getting them used to science. And we try to do limited procedures so that they have to think about what they're doing and come up with ideas on their own, kind of like what my dad used to make me do. So just trying to build that scientific inquiry and also let them ask us questions kind of like this about what we do in grad school, what it's actually like, what our day-to-day is, that kind of stuff, which has been really cool to see them get interested. We also are working on expanding to younger students, going to like elementary and middle schools, doing demos and stuff there for the same purpose, and just, being an example and someone that they can ask questions to, because I didn't have anyone who I knew who went to grad school who I could learn from and even know what it was. And it was this like crazy thing that I hadn't even considered until I was supposed to be doing it. So just being somebody for them to talk to, basically.
No, that's wonderful. That's a great mission, and that's great that you can do that during your graduate lab studies too, because heavens knows you're probably in the lab a lot. So especially when you're thinking about synthesis.
Yeah.
So we talked a little bit about future career and what you kind of think about doing. I mean, what does a person traditionally with your sort of research background probably do?
Yeah, that's definitely fair. I think I'm kind of in a weird spot, honestly, because I do a lot of organic synthesis, but I'm not an organic chemist. Because if I was, then a lot of them go into industry. If you're not a professor, there's a lot of like pharmaceutical companies you can work for and stuff like that. Or agricultural, that's big. And I'm thinking of the Indianapolis ones because that's where I am. But those are two big ones that people go into with more materials, or like I know the guys in my lab who do electrochemistry, they look at national laboratories. They have a lot of cool research that we're doing here. But I'm kind of in between, so I'm not really sure where I'm supposed to go, I guess I'll say. But yeah, there's a lot of different opportunities and stuff that are really cool.
I like that. My photochem teacher, he had a lab, in one of his little like arms of his lab. Most of it was photochem, but one little lab was making gels for art history. And so they would actually synthesize the gels, then put the gels on paintings and pieces of art for conservation purposes. And so that was always just kind of like fascinating to me. I couldn't handle organic or photochemistry by any means. I just didn't understand it with the little coming in of the light and then the acceleration of what is happening here. But it's like cool when you actually can do it and apply it, to your point. But yeah, I mean, it's kind of like the world, as I said before, the world's your oyster and what you can do. And, you can go the application route, you can go more of a fundamental route, sort of things like that. So that's always exciting. If you were to reflect on, and you obviously do mentoring, if you were to talk to Brianna from 10 years ago, sort of what would be your words of wisdom that you would impart on her?
Yeah, I think as far as like specifics at Colgate, I would have started research sooner. I didn't do it until like the summer before my senior year, just because I didn't even know anything about it. So I think doing that earlier, if you're interested in it, is a huge plus, because you can learn if you like it earlier, and then you have that experience and learn what you like. And then coming into grad school, I was very intimidated, didn't know if I could do it. So I think I would just say that everybody feels like that and it's okay, and just kind of give myself a little pep talk about that.
I think that's fair. I started when I was a freshman, and I had no intention of doing it long term. And it turned into something that I really enjoyed. So yeah, I agree. Plus the awareness that it's around, that you can do it, and you can do it when you're also, leveraging your classes, and yeah. So I love that. With that, Brianna, it's been such a pleasure speaking to you, not only about your journey thus far, what was your inception into entering the STEM fields, and then where your research is going. I think that's way, way cool. I think clinical trials in cancer treatment is definitely like the forefront of a lot of people's minds, and where science can really better the human population, let alone the population in general, I think. And so it's really fascinating work. So again, thank you for joining us today. It's been great. And then to our listeners, thank you again. And never forget to ask yourself, where does your journey stem from? Bye, everyone.